Now we are moving on to chapter 15. It is on multiple integrals. So we looked at basically partial derivatives, and this concept we'll look at integration and what we call multiple integrals. So first we'll start off in chapter 15.1, which is just defining the concept of iterated integrals. So 15.1 is iterated integrals. So first we'll go review just the basic setup and concept of a single variable. So first recall that if you have the definite integral from a to b of f of x dx, so that may be defined as follows. So one, what we do, so this is kind of just a review of how we look at it. We look at the interval from a to b. So we take a to b, and oops, let me back that up. So first we partition a to b by choosing, and this is just an arbitrary partition, a equals x naught, which is less than x1, etc., less than x2, which is less than, we go all the way to x sub n, which is equal to b. So we do that partition, and then 2, we say for each k, so it's an arbitrary interval in there, select any number w sub k in that interval. So we say x sub k minus 1 to x sub k, and we call that the kth interval. So that's some arbitrary value in some kth interval that's in here. So some kth interval in here, we choose w sub k in here. So this is all review. This is the definition that we would have used. And then 3, we form a Riemann sum and then it would be the sum over all the k's of f of w sub k delta x sub k, where the delta x sub k is equal to this interval. So that delta x sub k, you just say x sub k minus 1 to x sub k. Oops, not the interval. Sorry, it's the difference. So it's the difference of x sub k minus x sub k minus 1, because it's successive one after the other. So if you do the next one minus the previous, you get a positive number. So that's what turns into your dx. And then 4, we do a partition, the norm of the partition. So if the norm of the partition, let me define that first. So if that symbol is the norm of the partition, and we define that as the length of the largest subinterval. So we say the length of the largest subinterval, then we get the definition. So then we say that the integral from a to b of f of x dx is equal to the limit as the norm of the partition approaches 0 over the sum of all the k's, f of w sub k, delta x sub k. So that's the definition of Riemann sum, of how you define the definite integral. And let's do some depiction of that. So you'd have your interval, so this would be like the real axis. And we may have the partition in here, so this would be like x naught, which is your a, and then all the way to x sub n, which is your b, and then everything else is, it's not uniform necessarily. So you have x1, x2, etc., x sub k minus 1, x sub k, etc. So that's your partition. So in single variable, you're going from the real axis r, and then you're basically mapping to another real axis. That would be your xy plane. So you partition P like that, and then you'll recall that you have the xy axis. It would look something like this. So here's your x and here's your y. So you have some curve or some function, continuous function like that. That's your f of x. Then you're doing the partition from A, say, to B, and you get the area under the curve, if it's positive, of course. So this is like your kth interval, and you get this rectangular piece right here. And your w sub k, let me zoom in a little bit, your w sub k is anywhere inside that interval. So there's your w sub k. And I won't write it in, but this would be your, right here would be x sub k minus 1 to x sub k, and then the length is that piece right there. And then times the height right here is your f of w sub k. So it would be here. And then so that's how we defined it and how we added everything up to get your Riemann sum. Okay, so now we want to consider a function in two variables. That's the next piece. All right, so let's go down to here. Now consider a function f in two variables. So now f of xy is going to be defined on some region in the xy plane, like we've discussed that already. So f of xy is defined on a region R in the xy plane. So we want to define, so we will define the double integral. Let me make that a little better. We want to define the double integral. We say over the region R of f of xy dA, and describe what that is. So we'll go through the same process as we did above, but now you're going to basically map your region R to a real axis. Okay, we'll talk more about that as we go here. Just remember that, and then what the integration looks like in particular. So remember what a function of f of xy might look like and how it might be mapped. Okay, but let's do this derivation first. So let's consider the region R in the xy plane. So let's draw over here that region. So draw on the xy plane like this. Because remember, you're always mapping the xy plane to a real axis, the z-axis. So some region R is in here, something like that. It's good enough. And then what you do is you take an outside rectangle that you place all the way around that region R. So you take some rectangle. Let's do it like this. You take this rectangle all the way up, all the way down. Close enough. That worked pretty well. Let's shrink that in a little bit. So like that, like that. So let's take that rectangle. So inside is your region R. And then we partition that outside rectangle. And I'll do this partition in a different, I'll do this in gray. So you take this and you basically try to make this partition, and I'll just do it simply, kind of rough, that way we're not too picky about everything. Okay, so this is some partition. Again, you can make it nicer if you want, but you partition the entire thing like this. We'll do a couple real nice and then speed it up a little bit. Not trying to make them perfect as I actually draw this thing. So some are smaller than others. And I'll exaggerate one right here. It was not an even partition, right? I'm doing a couple that are exaggerated. So when you do the norm, of course, the largest one shrinks to 0. Same sort of idea. So let me zoom in a little bit on that. So you can see here that, I don't know, maybe this one is the largest rectangle. And that what we'll define is the norm will be the length of a diagonal. So we'll do a diagonal like that. The norm is going to be the length of the largest diagonal, and we'll shrink that to 0, which makes everything else basically shrink to 0. Getting a little ahead of myself there, but that's what we'll be doing. So we'll pick an arbitrary interval in here, a point in that. So we're going to define R sub ij as one of those rectangles, and a particular point in there, say right here, will be my, we'll say U sub k and V sub k. Okay, so we're going to do that. So this is just the setup. We go from A to B, and then we go from C to D for the rectangle. Okay, and so then in 3D, let's do a 3D version of that. Might look like this. And like this. So here's your X and your Y and your Z. And then in here, you'd have your rectangle. We'll try to match that picture like that. And that needs to be parallel. What we could do is just copy that and then paste it over here. So it's the same exact length. And then the same thing with that one. We can copy that, paste it here, and then you get that rectangle in there like that. So the region is inside that. Well, not the exact one, but you get the idea. That's the concept. So you get this region R in here. So that's my R. And then this is what you are going to partition up like that and like that. Okay, so you get that sort of look, and then you have one of your values inside here is your U sub k, V sub k is your point you put into the function. And similarly, this goes from A to B and then C to D. And so let me draw in the region R so you can see it a little better in here. It looks something like this. This is your region R that's inside And now that's the setup. That's the kind of the picture. All right, so now we want to go through them more carefully and define the double integral similar to above that we just did. So we'll do one at a time. We're going to partition AB and partition CD, and then set up our sum. So here we go. Partition